Hello everyone, welcome back to my channel. After a long time back, I'm making another video, and it is a very important video for the students who want to know what is the conversion of product from a reaction by taking NMR of the crude. So here, let's take an example. So methoxybromo compound, by making it as a Grignard reagent by reacting with magnesium iodine catalytic amount in THF and reflux, then it will make a MgBr like Grignard reagent, this methoxybenzyl magnesium bromide, and then this diketon react with this Grignard reagent in situ, like you add, once it is formed with the Grignard reagent, then you add this diketon dropwise. Like maybe you can dissolve this compound in THF and slowly dropwise, then it will form this reaction. It depends like amount of this reagent, so it is a limiting reagent, so you have to add to make this dimer, you have to add exactly 0.5 equivalent. So but it will be better if you add 0.45 equivalent, little bit less, then it will control to make dimer. Otherwise, if you add excess of these, then it will actually form the, most of the product will form the monomer. So one side attacked and another side is not. So it is the crucial limiting reagent, so you have to add a little bit less than the half equivalent. So I used 0.45 equivalent of this diketon compound. Then the reaction formed this dihydroxy compound. So to get the idea from the NMR how much you should get, so you need to know the structure. Like you definitely design your molecule and you know like which molecule you are trying to make, and from that molecule try to find out what are the possible proton NMR you will get. Let's see this structure. So although it is a symmetric molecule, but it has two chiral carbons. So one is here, this is one chiral, and another is this, another chiral carbon, and it has these two hydrogen and these two hydrogen. So if you replace one hydrogen with another group, and if you replace one hydrogen in another group, so these will form a diastereomer. So due to this diastereomeric proton, so although it is a symmetric molecule, you should get one methoxy group and one methyl group, but since it is diastereomeric proton, it has diastereomeric proton, so you will see these two methoxy separately, also these two methyl separately, these two hydroxy separately, and these aromatic proton you will see average proton. So how many different aromatic proton is here? 1, 2, 3, 4. Here also 1, 2, 3, 4. So these 4 types aromatic proton you will see in the aromatic region, total 8 proton. So if you take, even if you take these 3 and 3 differently, but still you will see all the aromatic proton as like average like 2, 2, 2, 2, total 8. So if you see, let's see the NMR example of NMR, then you will understand what I'm talking about. So let's go to the NMR. So first, to understand, I will show the pure NMR, and here I showed you the that methoxy. You know that how the NMR work. So if you have less idea about the NMR, so before I starting, I can show you something. Just go to my channel and see these videos, especially organic compound analysis episode 5, episode 4, organic compound analysis episode 3, episode 2, and organic compound analysis episode 1, carbon NMR for organic compound last part, proton NMR organic compound structure, proton NMR organic compound structure. So these videos I explain detailed how to detect the proton NMR, protons and how to detect the carbons, how to get the structure from a certain spectra, how to elucidate the structure. So you will get a clear idea on those videos how to determine the molecular structure by using carbon NMR and proton NMR, and also a detailed knowledge on the carbon NMR and proton NMR. So let's go back to the NMR. So here this is the NMR. So if you see this methoxy carbon, since this methyl proton is next to oxygen, so it will always go downfield. So if you go like bigger ppm, so it will be downfield. So in that case you will see two different methoxy proton. So one methoxy proton, another methoxy proton. So this is a pure compound, and I just assigned the peak, like one is 3.79, another is 3.80. It is a pure compound. And also if I go like full spectra and zoom it, so here you will see these methyl and this methyl here. One is methyl here and another methyl is here, 1.45 and 1.50. So first of all, from the molecule you have to find the signature peak. So by that way you can integrate your full spectra based on your signature peak, and then you can decide a certain region to calculate how many proton you are getting and how many proton you should have. It's a very simple and easy way, but you have to understand the molecule and you have to find the signature peak. So you can take this methoxy as a signature peak or this methyl as a signature peak. It's better to take the clean portion, clean region. So if I go to the actually crude NMR, so this is the crude NMR, and we don't have any signature peak in the aromatic region, so we are not looking any peak here. So let's see in the methoxy region. So methoxy region has actually 1 2 3 4 5 peak. So if you know from the pure compound, or if you are making just for the first time, so you even don't know like which are the part of this compound. But if you know the pure compound, then you can know the this peak and this peak are the part of this compound, and those are like not part of this compound. So for the first time, like when you don't know like which are the proton, so try to find out a signature peak where it is like pure region, so kind of clean region. So here, although you have a couple of many peaks, but clearly those two are like understandably like methyl peak. So in the molecule, you know, we have a methyl group here and there is another methyl group there. So those two methyl group, you can think one is methyl is this and another methyl is this. So you can initially integrate this methyl group. So let's see if we take if we integrate this methyl. So click I, then you can integrate this part, and it is showing 1 first time. Then click on this and right mouse click, edit integral, and put 3 and click enter. Then it will show 3, and then you can integrate this part. It will show a little bit more because due to the relaxation time, sometimes aliphatic peaks always show a little bit higher. It's fine. So take these two and then make full spectra, and click Z for the zoom, and then you can make integration in this area also. Now click I again, integral. So you can integration this part, and total this part, although it is not mandatory because you know we selected those methyl as a signature peak. This methoxy we are not taking as a signature peak, although you can take, but it is showing a little bit more. Then go to the Z, like zoom, and make it full and integrate the aromatic part based on the signature peak, like methyl peak. So now I am integrating this. So here I am integrating this whole part, and I will integrate this whole part, and I also integrate this whole part. So because based on the signature peak, I will integrate the whole aromatic part, and in the aromatic region I know how many proton I should get and how many I am getting now. So this part, zoom again and then integrate again. So I will integrate this part, this, and this is actually chloroform peak, CTCl3 peak, and I will integrate this, or actually this is chloroform peak, so it is not correct. I will delete this part, delete integral, and then do integration from here to there, total. So these are the integration values we have found. So make it fully spectra and zoom this part. So based on that methyl group I get this. Now go to the pure compound one. So again I have this 2-methyl here, so I will integrate this part. So I will integrate this as a first this, and it is showing as a 1, so make it edit integral and put here as a 3, then click enter, and then integrate this part. It will show a little bit more like 3.82, but it is also 3 proton. So first one as a 3, just make this is a signature peak, then go to there. You even don't need to integrate this part because we are not considering to calculate this part, but still you can check like how many proton are showing from this each peak. So it is showing 3.7, another is 3, normally it is 3, so it's close. And again aliphatic proton always showed a little bit extra, sometimes it's okay. Now that can also impact in the aromatic region also, because this is like taking a little bit more or high, so it's fine. So in the pure compound, if you calculate it, so now integration this part, so calculate, this is 2.28 actually for 2 proton, and this is 2.38, this is 2.30, and this is 2.10 something. Now our integration is done. So here, look here, this is a doublet of triplet, and this is upfilled, and this is like downfilled, more downfilled. So clearly this peak should be you can understand which is this peak. Actually this peak, maybe make it more zoom, then you will understand more perfectly. Let's say this peak. So this peak, it should show as a singlet. So this peak, actually this hydrogen, but it has a metaproton here and also a metaproton here. That metaproton is splitting again this proton, that's why it is splitting multiple times. So this is that proton, and this proton, it has one neighbor directly, so it should show as a doublet, and then it has one metaproton and another metaproton, like 1 2 3, so metaproton, 2 metaproton, so doublet will split again as a triplet, so doublet of triplet, so, or like you can say triplet or doublet. So it could be this one, this doublet of triplet, this doublet, so doublet of triplet. And this proton has 2 proton neighbors, so it will show you triplet, and then it also could be affected by this, but directly triplet is kind of okay. So this will be this one. So like normally it will show a triplet, but that also splitted by this proton, so it is there. And now this proton is next to this oxygen, close oxygen, so it will be like more downfield, and it has one neighbor, so it will be a doublet, but it has one metaproton and another metaproton, so doublet of triplet, so it will show this proton. Anyway, it is easy to understand. So you will have total 8 proton in the aromatic region, but you are getting a little bit more. So let's see what is the total you are getting. So here is 2.28, so 2.28 plus, and here 2.38, 2.38 plus 2.30, 2.30 plus, and here 2.10, 2.10. So you are getting 9.06 in the pure compound only for the aromatic region. So keep this in mind. So let's see our equation. So equation here I will say 9.06, 9.06. And now go to the crude NMR. So in the crude NMR, how much we totally get? Okay, let's calculate it, how much we get it. So first is 3.31, so 3.31 plus 7.80, 7.80 plus 1.45, 1.45 plus 3.13, 3.13 plus 1.74, 1.74. It is 17.43. So let's go here, 17.43, 17.43. Now the percent conversion you can get, it will not give you the exact amount, but you can get close amount, like how much it is converting, and based on that you can continue your reaction more time or less time, something like this. Sometimes it can convert like 100%, sometimes it depends on the proton NMR. So you can calculate the number of protons supposed to have in pure, that is we found like normally it should have 8, but according to our calculation we get 9.06, so take that that is as a pure. And number of proton you found in crude, so number of proton we found in the crude, and we are, remember that we are considering only the aromatic portion, so we are getting 17.43 times 100. So in that case this value will be changed actually, definitely. So find this 17.43 times 9.06, so it will be 51.97, like around 52, so 51.97%. So from this NMR you are getting a idea like how much your product conversion here from this reaction. So today this is a video I think will help you to understand or to calculate the percent conversion of a molecule, and definitely ask me question like if you don't understand, and I hope it will help you to calculate the conversion of a reaction. And remember that there are more complicated way you can calculate, like by taking the mole ratio and many other things, but what I showed, it is very simplest version and simplest way, like when you are doing reaction and you just check the reaction for monitoring after a couple of hours, and then check the reaction, and that reaction check NMR, like crude NMR, you can calculate the percent of conversion from that crude NMR. So here you can see the total NMR of the crude. So here is the crude NMR. So we are not calculating all those things because since we have a certain number of aromatic peak, we know we should have, but in the crude also it has something extra thing. So you can calculate all the aromatic peak, and in the pure NMR you can calculate how much you are getting as a pure compound. So in that case, easily you can calculate the how much you should have over in the aromatic over the how much you are getting. So you will get the percent conversion. So thank you for watching my video and for supporting all of the people all over the world who is watching and asking me many questions, and I'm kind of busy still. I'm trying to answer all the questions when I get time. So on this video, if you have any question, please ask me. I will happy to answer your questions. Thank you for watching, and please subscribe and share my videos to the people who are learning chemistry and research. It will help to grow my channel, and also people will be benefited. Thank you. Bye now.